Welcome back. So last time we solved a question using the laminar and the turbulent shear stresses. We calculated the laminar viscous sublayer thickness, then we calculated the center line velocity using those equations of turbulent velocity profile, and then in the end we calculated the ratio of turbulent shear stress to laminar shear stress and found out that the ratio is more than 1000. It was almost 1217, indicating that in a turbulent flow the ratio of turbulent shear stress to laminar shear stress is very high. Okay, so in turbulent flow the dominating shear stress is due to the turbulence. Now we are going to start a topic, dimensional analysis of pipe flow. So pipes are generally considered rough and they have a roughness that is so they have this roughness, and because of this roughness there is loss of energy due to viscous flow in the straight element, and this loss that happens due to the viscous flow is called the major loss in pipes. All right. So there are two types of losses in pipe, which is one is major loss and the other is minor losses. The minor losses happens due to the pipe components. Suppose for example there are junctions at pipes, or there is a bend, or there is a contraction or an expansion, then also there will be some loss in the energy contained in the turbulent flow. Okay, and those losses are called minor losses. So for major losses during the dimensional analysis, we say that the pressure drop should be a function of the velocity in the pipe, diameter d, length L of the pipe, mu, the viscosity, and the density of the liquid. Here we have an additional element, that is roughness height epsilon. Okay, this is a new thing that we are going to take into account. Earlier we said that the pipes were smooth, there were no roughness element. So pipe, so there are roughness elements like this. In principle there are roughness elements like this. All right. So if we do the dimensional analysis, then we first write down k, how many, 1 2 3 4 5 6 and then 7, and r is 3. So how many dimensionless term? K minus r, that we are going to get 4 dimensionless term. If you do the Buckingham pi theorem analysis, we are going to get, so this is, as I said, was the roughness element epsilon. This is the roughness element as I showed you before as well. We will get 1 dimensionless term, 2nd dimensionless, 3rd and 4th. All right, as we said, k minus r, 7 minus 3, 4 dimensionless term. Okay, and I ask you to do it as a homework question. If you have any problems, you can ask us about that in the forum. All right. So this is the general equation for pressure drop for a pipe flow with roughness element of epsilon e. All right. So again we write down delta p by half rho v square is a function of rho v d by mu, L by d and epsilon by d. All right, this is what? This is Reynolds number. All right. This we know from before, rho Vd by mu. Now we already know from before the pressure drop is proportional to the length of the tube. Alright, so we can take L by D outside and we can write delta P by half rho V square is equal to L by D as a function of Reynolds number and epsilon by D. How this depends we still don't know, right? Until now, I mean with the topics that we've covered, we still do not know. But other things we know, half rho V square L by D, Reynolds number also we know. Okay, we do not know how to find epsilon, and we also don't know how this function is dependent upon Reynolds number and epsilon by D. Correct? But that we will get to know in the upcoming slides. So again we write down the same equation, delta P by half rho V square is L by D and a function of Reynolds number and epsilon by D. So what we bring L by D on the other side, right, and define. So if you take D on this side and L here and term is at F, so F is nothing but delta P into D divided by half L rho V square, and this we call friction factor F. Alright, so F is a function of Reynolds number and epsilon by D. Alright, so as I wrote, F is equal to a function of Reynolds number and epsilon by D, and if we are able to find this F, we can easily calculate delta P as F into, because see, if you use this equation again, we can write delta P is equal to F into L by D into rho V square by 2. So if we are able to calculate this F, we know L, we know D, we know rho, we know V, so everything will be calculated. So the challenge is now finding F, and this is valid for horizontal pipes, this equation. Now for a fully developed laminar flow, we already found out that what that F was, it was 64 by Re. From our previous lectures in pipe flow, we have derived that F is equal to 64 by Re for fully developed laminar flow. But for fully developed steady incompressible flow, we also know that the head loss is going to be, if we assume delta P is the head loss, and that will transform into energy loss equivalent to rho g h. So HL major can be written as delta P by rho g. Alright, just concentrate on this. So this is the head loss major, and delta P by rho g can be, so if you use this equation and divide it by rho g, so what are you going to get? F will remain same F, L by T will remain same, rho and rho gets cancelled, and we can get F into L by D into V square by 2G. So the major head loss is going to be FL by D into V square by 2G. Alright. So the major head loss, L we know, D we know, V we know, and G is a constant. So again the problem is we still don't know F, but for F we know it's a function of Reynolds number and epsilon by D. Alright, and this particular equation is called the Darcy-Weisbach equation, a very, very important equation for the major head losses in the pipe. So how do we estimate F? For F, if we would know Reynolds number and epsilon by D, everything would be the recipe would be available to find out the friction factor F. So, this, before going to how to find out this epsilon by d, I have a small class problem which we are going to solve. All right. So, the question says that water flows through a pipeline whose diameter varies from 20 centimeters to 10 centimeter in a length of 10 meters. If the Darcy-Weisbach equation factor is assumed to be constant, so F is given constant at 0.02 for the whole pipe, determine the head loss in friction when the pipe is flowing full with a discharge of 50 liters per second. So, we are going to solve this question. All right. So, we say consider a stretch of length dx at a distance x from 20 meter diameter end. All right. This was a 20 centimeter diameter end, okay, and this was 10 centimeter. So, we assume at a distance x a strip of thickness dx here. All right. So, dhfx will be f L, so L is here dx by, so v square by 2 gd. All right. If we write in terms of q, we can write f friction factor F q square dx divided by 2g pi by 4 whole square into d to the power 5, because q square will, v square will be q square by a square and a is d to the power 4. So, we are going to get this equation where the, here this is the diameter d at distance x. All right. So, we need to find what that d is, and d can be written as, see, it will be varying from 20, right, 20 centimeter. All right. So, we can write, to convert into meter, 1 by 100, and this will come 20 minus x in meters. All right. This is the diameter. So, we proceed forward. So, dhfx will be 0.008263 f into q square into 10 to the power 10 dx divided by 20 minus x to the power 5. Okay. This will be, if you calculate, it will be 41313 into dx by 20 minus x to the power 5. So, total head loss will be integral of dhfx from 10 centimeter to, I mean from 0 to 10, right. So, total head loss is going to be 41313 integral 0 to 10 20 minus x to the power minus 5 dx, and total head loss HF is going to be 0.968 meter. So this is how you solve this question. All right, a very simple application, because the Darcy-Weisbach friction was already given. All right. So this is one question. So until now what we have done, we have obtained the pressure drop, and as a function of another quantity, pressure drop was as a function of Darcy's friction F, where F is some function of Reynolds number and epsilon by d. In laminar flow, fully developed laminar flow, it was only a function of Reynolds number as 64 by Re. But before going into that, we just solve, if we are given that friction factor F, Darcy's friction factor F, how are we able to apply these formulas of DHFX to find the head loss. Now there is another question. It says that in a horizontal pipe of diameter d, which is carrying a steady flow, there will be a pressure drop in a length L of the pipe. It says, prove that if bed shear stress is tau naught is equal to rho u star square, then u star can be written as nu into under root f by 8, where f is Darcy-Weisbach friction. And then a question is given that water flows in a 2 centimeter diameter pipe. Now taking the kinematic viscosity of water as 0.0098 Stoke, calculate the largest discharge for which the flow can be definitely laminar. So largest discharge will be at largest velocity, that means we will have to utilize some Reynolds number, and then in the end it says what is the boundary shear stress for this discharge. So we will go one by one for the solution. So the first part is pretty simple. You have to equate the frictional resistance with the difference in pressure forces. Okay. So instead of delta P, we write P2 minus P1 into pi d to the power 2 by 4 is equal to tau naught into pi dl, correct. So tau naught using this can be written as P2 minus P1 into d by 4l, or minus delta P d by 4l, because P is P1 minus P2. Now designation, tau naught is f by 4 rho v square by 2. Here f is back friction. So under root tau naught by rho is equal to mu star is equal to v under root f by 8. All right, this is how we get. So we from this equation. Now starting with the second part, part B. the largest discharge corresponds to the critical Reynolds number, which is for the largest, it can be for laminar, it can be maximum 2000. Remember, Reynolds critical will be 2000 is equal to Vd by nu, which will give us velocity as 2000 into nu is 0.0098 into 10 to the power minus 4 divided by the diameter 0.02 gives us 0.098 meters per second. Therefore, Q will be pi by 4 into diameter whole square into this velocity. This is going to be 0.03079 liters per second. Instead of meters, we have multiplied 10 to the power 3 and made in liters per second. Okay, or if in terms of meters, minutes, you can simply say multiply it by 60 and say 1.847 liters per minute. Okay, so this is the largest discharge. Also, F can be written as 64 by Re, which is come 0.032. So U star can be calculated at under root F by 8. F is 0.098. We have already found out F was 0.032 divided by 8, or 6.198 into 10 to the power minus 3. Similarly, tau naught will be rho U star square, which we have calculated, and it will come out to be 0.0383 Pascal. All right. So this is yet another simple question of the Darcy-Weisbach equation, very simple. So we go back, and there's one more problem. So this is the last problem before the end of today's lecture that we are going to do, and it says is design the diameter of a steel pipe to carry water with mean velocity of 1 meters per second. The head loss is to be limited to 10 centimeter per 100 meter length. The effective roughness height can be taken as 0.45. Now use the following empirical formula for friction factor. So in this question, you see we already have been given ES, this thing. Okay. So F we can calculate. There is still not, we have been given the functional dependence of F. How to find out F? So it's a pretty simple problem. If we are given F, we just need to follow the basic steps. How do we solve this problem? First, we find the Reynolds number. So Vd by mu, and V1 meters per second, diameter d, let it be this, and mu is 1 into 10 to the power minus 6. So it becomes 10 to the power 6d in terms of diameter. We have already been given ES, that is 0.45 into 10 to the power minus 3. Now if we substitute, then is this in this value 0, the F which we have given, because most of the things we know already, into 0.45 into 10 to the power 3 by d, because d is we don't know, that is what we have to find out, to d. All right. So F can be written as In final it can be 0055 plus 6.812 into 10 to the power minus 3 divided by d to the power 1 by 3. And HF will be FL V square by 2 GD. So head loss has already been given. It says 10 in 100. That is what it said. If it says the head loss is limited to 10 centimeter plus 100 meters per of length, right? So head loss has been given. So we can write 10 by 100 is equal to F by D into 100 into 1 divided by 2.981. This will give us F is equal to, in terms of this, is 0.01962 D. All right. So we have two equations for D. All right. Sorry, two equations of F. So the value of D is obtained by trial and error from above equations of F. Okay, and F is found out to be 0.0133 and corresponding D comes out to be 0.678 meters. All right. So if there is a practical problem, in practice we would use next larger standard size, because the pipe diameters does not come, it's very difficult to design 0.678 meter, maybe 0.7 meters is available. So we are not going to use 0.678 but the next higher size available. All right. So this concludes this particular question. Moving ahead. So before we close this class, I would like to take this, what is the equivalent roughness for the pipes? Epsilon. Sorry. What is epsilon? So epsilon is a material property, and this epsilon can be obtained for practical senses with tables like this. Here it is given that for riveted steel epsilon varies from 0.9 to 9.0. Concrete, it is going to be 0.3 and 3.0, and wood stave, for example, 0.18 to 0.9. So for every type of pipe a corresponding epsilon will be told to us from before. For your purpose, most likely the epsilon will be given in the question, because otherwise you will have to, otherwise you will have to look it from the table. If we don't give you epsilon, we will give you the table. So you look which type of pipe is there among these, for example, and you find out epsilon and then proceed with your problem. So now you remember F, the Darcy friction, was a function of Reynolds number, epsilon by D. Reynolds number we know how to calculate. Epsilon would be given and D would also be given, right? So we know everything, but how it is dependent we don't know, correct? This part we still don't know. So to answer that we have to proceed further, but before that there is a class problem. This is one question that we would like to do again, but I would like to close this lecture now and start our new lecture by solving this particular problem. Thank you so much for listening, and I'll see you in the next week.